Welcome to Spring LIB.
We are given this list of standard reduction potentials for these four half reactions, and we are told that in the electrolysis of an Na2SO4 solution, that we want to determine which of these half reactions occurs in the anode and which occurs in the cathode. We know that oxidation will occur in the anode and that reduction will occur in the cathode. And so since we have a solution of aqueous Na2SO4, that must mean that we have aqueous Na plus ions, aqueous SO4 2 minus ions, and also water. And now we need to use these standard reduction potentials for the half reactions involving these species in order to determine which species will be reduced and which one will be oxidized, so we can determine which occurs in the anode and the cathode. So starting with Na+, we know that we can only reduce Na+. We cannot increase a charge of Na+, and so the only half reaction that we can have out of the four given half reactions for Na+ is a reduction by adding one electron. And we see that out of the four, it has the smallest reduction potential. And we also know that for water, this can be either reduced or oxidized. If we take this reaction and reverse it, then we can see that we can oxidize water. And for this reaction, this represents the reduction of water. And for SO4 2 minus, we know that we can only oxidize that. We cannot increase the charge of that. We cannot add more electrons to SO4 2 minus. And so if we reverse this top reaction, that would represent the oxidation of SO4 2 minus. So Na plus can only be reduced, SO4 2 minus can only be oxidized, and H2O can be either reduced or oxidized. So now we need to determine which reaction will occur for the reduction and oxidation. So starting with the oxidation, which occurs in the anode, we know that that will correspond to either the reverse of this first reaction, where we have SO4 2 minus being oxidized, or the reverse of the second reaction, where we have water being oxidized. We are given these standard reduction potentials, and that means that a higher value for a standard reduction potential means that that half reaction has a greater potential to undergo reduction than a half reaction with a standard reduction potential that is smaller than that. And so the opposite is also true. So when we reverse these reactions, those correspond to oxidations. And so the reaction with a smaller reduction potential would therefore have the greater oxidation potential. And because of that, we know that that means that water will be oxidized rather than SO4 2 minus, because it has a greater potential to oxidize based on its smaller potential to be reduced between those two oxidation reactions. So therefore we know that water is oxidized, so that reaction, the reverse of the second given half reaction, will be what occurs in the anode, where we have 2 H2O going to O2 plus 4H plus 4 electrons. And now for the cathode, we know that in the cathode, the reduction reaction occurs. And so we can either reduce Na plus or water. And we are given the standard reduction potentials, and either this half reaction or this one will be the one that undergoes reduction. And when we compare the two, we see that the reduction of water has a greater value or a less negative value for the standard reduction potential than for the half reaction showing the reduction of Na+. And so therefore, due to the greater reduction potential, water has a greater potential compared to Na+ to be reduced. And so therefore, it will be reduced and take place in the cathode. So the reduction of water takes place in the cathode. And again, that reaction is 2 H2O plus 2 electrons goes to H2 plus 2 OH minus. So water is both oxidized and reduced when we electrolyze an Na2SO4 solution.